Hello, this is Jeffrey Fox again with a small lesson group on how to do PageRank using Python. And this is basically a data analytics, a technology used to support Informatics or big data processing. And this is just one of your library of data analytics you will have available to you as you do your big data processing. So here are the actual resources needed by this lesson. The first set correspond to calculating PageRank given a set of pages with information on which page points to what other pages. That's described at these websites I gave here, and the code which has both this sort of basic functions and the driver is in PageRank2.py available on your resources. We also have some code which you type in the website URL and it will tell you what PageRank Google thinks it has. All right, now let's come to the sort of basic data analytics. We did discuss PageRank back when we did web search. And the key thing for finding the PageRank is the adjacency or linkage matrix. And that's Aij, and Aij, where I runs from 1 to 6. We probably need a pointer. So here's I of 1, here's I of 6, here's J of 4, and J of 6. So what does A14 equal to 1 mean? It means that 4 only points to one other site, and that site is number 1. So that's that one there. 5 does not point at 1. 6 does, and 6 only has one URL on it, so it just points to one site. So that's what those ones here are. Let's do one other case. Let's look at this half here. That's this is I equals 6, so it's talked about site 6. This is J equals 1, which means it's to do with what 1 pointing at this site. So 1 has 2 sites it points to, so each has weight a half, and that's that half there. One of the ones it points to is 6, and the other one it points to is 2 up here. So these matrix entries reflect directly the graph that's shown here of what points to what. So you take that matrix A and we form a new matrix M, which is damped by adding a matrix S, which corresponds, if you remember in our original discussion, to the chance that somebody will type a random URL in the header of the web page. And so you form a new matrix M, which is D times A plus 1 minus D times this matrix S, where everything has, every entry has the same value, which is in this case 1/6. And the folklore says that the good value of D is 0.85. And there's 85% chance that you'll actually follow one of the links on the page, and 15% chance that you'll give up and go to a totally different site. Then the basic algorithm is actually very simple. We set up an initial matrix, initial vector X. X is going to be the vector of page ranks for each of the pages. So the first position of X0 is the rank of site 1. The 6th position of X0 is the rank of site 6. And the page ranks have to add up to 1 in the simple formalism. And so you always normalize these vectors so the sum of the components, which are positive, add up to 1. And so that's in Python gotten by this command over here, where n is the number of sites, 1s of n over n. And then we actually just iterate the following equation. X0 is replaced by m times x0 times the norm of the new value of x0, which should really say m times x0 in that equation. So we use in this PageRank 2, it has all these methods, and the first method is shown here, and it just iterates, because remember we have to keep on doing this. You're meant to form the A is actually really here M. It's the whatever matrix you're analyzing. So it's just an it's not the actual adjacency matrix. It's the modified adjacency matrix. You form the dot product of x0 with A, and then you replace x0 by x0 divided by its norm. And if you have the option 1 here for the norm, it says that this particular norm is such that the sum of the elements of x0 is 1. Notice that in many other applications, you take a different norm, which is the sum of the squares of the components is 1. Here you have the sum of the components is 1, because we're dealing with probabilities and not probabilities add to 1. The squares of probabilities do not add up to 1. The function I took from the web is slightly inaccurate. It just fixes the number of iterations. It's actually probably better to just stop when you reach a certain threshold change, and we'll come to that later on. We use these two built-in Python methods, the norm method, which I pointed out as its option. If the option is 2, it calculates traditional Euclidean norm, and for option of 1, it calculates the sum of the moduli. And in this algorithm, the values of x, in fact, are all positive, so the modulus doesn't actually matter. But we, as I mentioned, need option 1. And we need this dot product of 2 arrays, or in his case, matrix times a vector. And you just look up and you find that you just have to do as we do there, do numpy dot dot of the matrix A into the vector x0. You'll get what people want, which is M, the matrix A times x0, matrix vector multiplication. I pointed out that I would view this as slightly inaccurate in that it has a fixed number of iterations, and that's really not terribly useful. If you actually already converge, you can add another parameter to this function, which gives you method base 1. I just added a 1 to the argument, and I added a threshold here. And when the normalization of the change in x which is x0, the x1 is set to the old value of x0 here and here, and then you just calculate the difference, and if this difference is less than the threshold, you stop. So this is just a minor change, which if you cared about it will save computer time. So that's then, this is then just a repeat of this function. We don't need to go through it again, but they actually in the page that I took from the web, they use 130 iterations. In the first example we do, the matrix A I gave you already, actually 20 iterations is more than enough. In other cases, you need more than 20.